and then I think it's time to move to the next speaker, who's PEDRAN ROUSHAN at Google Quantum. He has done great work in different areas of condensed matter physics, quantum information, superconducting qubits, quantum computing, quantum simulations. So it's a great pleasure to have him here. And then it's here 1:20 in the morning, and for you it's also early in the morning, but a bit later.
Yeah, hi. Yes, are we 10 minutes behind or?
Yeah,
well,
I think we're about 10 minutes behind. Sorry. Yes.
Yeah, no, I have a flight to catch, so I apologize. Right, probably about 9:45 or something. I'm going to stop and I have to leave. But let's get started.
It's okay. It's okay. We can just go ahead and start, and then.
Yeah. Let me see. I'm not a Zoom person.
Oh, you
So let's see
need to exactly select the screen.
Let's see what we got. Is it okay now?
Great, fantastic. Please go ahead.
Yeah, it seems you guys don't have the tradition of stopping in the middle. I don't see any chat box or anything, but if you guys want to stop me, that would be perfectly fine. I have okay. So my plan for the talk was to start with the quantum supremacy beyond classical experiment, and then get into an instance of NISQ. I don't know if there is a preference to emphasize one versus another, but I can just get started, see how far we're going to get.
Since you need to catch a flight, feel free to go fast on the easy part at the beginning.
Yeah, okay, sure. Yeah, so I'm a member of the Google Quantum AI team, and as some of you may remember or heard about, in 2019, we put a manuscript out that we claim we have outperformed a classical computer on a very specific task. So first, I'm going to talk about that very specific task and how we did it. And by explaining that, it should become clear the shortcoming of that experiment and things that we have to go beyond that. So the idea began maybe a decade before that by works of John Preskill, maybe put it very more to sharp focus and make it very clear, emphasize that if all this quantum computing and all this quantum promise is going to work, we better show at least one instance of something that really can outperform classical computer. Maybe we find one example of something that do something better than classical computer, because the quantum processors that we have, they are noisy, they are not reliable, and there are lots of technical and engineering and system, putting a large system together that we don't know. So can we come up with an experiment that we can outperform a classical computer? So that was the thinking behind it. And this is the example, although it's a bit contrived and it become clear on that regard. This is the experiment we did. We picked a grid of 9 by 6 group of qubits. One of them broke, so we have 53 qubits total. And we start with a wave function, known wave function. The quantum state of the system was at 0, 0, 0, 0. And then we evolve it with a given set of unitary gates. You randomly choose these gates and you evolve the wave function according to the wave function evolves according to these gates. And then you start sampling bit strings at the end. These bit strings, according to Born rule, associated with the wave function of the system at that instance of time, at that instance of cycles. And you can get a bit string, which is probability is set by the wave function amplitudes. And you can get bit strings, maybe 1 million of them in few minutes. And the claim of the experiment at these bit strings are truly and loyally coming from the evolution under this unitary, and no one can produce bit string with such a degree of fidelity from a big wave function coming from this evolution with the rate that we can do. So for quantum processor, the rate is fixed no matter how many qubits, how many depth here is negligible. But for classical computer, this become exponentially hard. But one thing I really like to bring to sharp focus is that if you have ever read that manuscript, we really put a large amount of emphasis on gate fidelity and fidelity of the operation and readout fidelity and whatnot. What I would like to say is that if these gates were, I don't know, by factor of 2 more, had lower fidelity, you would not be able to perform the claim would not stand, meaning the fidelity is very important. You cannot have a faulty quantum processor and ask your quantum computer, ask your classical computer to do exact wave function. You really have to put them on equal footing, and in this regard, the fidelity become very important. So these are the number to keep in mind, and it also tells you how far in depth you can go and what kind of NISQ algorithm one can anticipate. But the two main concepts that we worked on to show, at least experimentally, the two main ingredients of the experiments are, one is the notion of complexity. We have to be sure the problem is complex. And the way it works to prove these problems are complex is try to map it to a problem which is complexity is known. And you say, okay, if this is not mapping there, then the polynomial hierarchy is going to collapse. But these things are usually done under lots of assumptions and whatnot. But then the thinking behind complexity is that you really have to, you are claiming it's hard because you really need a big volume in the computational space to carry the computation. And if you simplify it or say confined to a region of the Hilbert space, you would not be able to do anything computationally hard. So for that, you have to break all the symmetries. And for that, the way to check it is that you're uniformly exploring all the available Hilbert space. So the icon I picked in here is like a motion of a billiard ball in a stadium, and the shape of this stadium or a billiard table, the shape of this table, you can see sets which regions you are going to go. And in one case, you would visit every part of the available space, and in one case, you would not. You would systematically stay away from certain regions. So this is the proof of complexity. I don't know if I may have data for it. This is providing intuition for complexity, meaning there is no symmetry left, and all the Hilbert space is therefore needed. Another is the notion of fidelity, as I mentioned, is a big deal, that you can show you can do the operation yourself with a high fidelity. Otherwise, creating a complicated dynamic is not hard. You can think about the motion of water or something, and if you do coarse grain it, you would not be able to predict its motion. So making complex is not hard, but it matters to be done with high fidelity in a sense. So here's the evidence. I'm going to go very quickly over this. It's mainly for you to be able to read the manuscript in your own, I guess. And here's the notion of where the notion of complexity comes from, meaning that let's consider a set of 6 qubits or 9 qubits or 12 qubits, and you run the gate sequence I showed to you. And then after a certain number of cycles, I forgot, maybe let's say 5 or 10 cycles, you look and you say, what are the probability of getting any of the bit strings, you know? And that's the horizontal axis, or the vertical axis is the number of time, or you can easily convert it to probability. And this is a distribution, look like a speckle pattern, look like nothing very peculiar. But what you could do, you can bring the bit strings that occurred more than others to the left and the least likely ones to the right. And now it has a shape, and there's a prediction about what this shape should be in the case that you're uniformly exploring Hilbert space. Imagine a wave function of the system at any instance of time. Any cycle can be written as a superposition of a bunch of bit strings. The first line is not anything complicated. And these bit strings are complex numbers, meaning bit strings have real and imaginary parts. Okay, so far there's no assumption to it. The uniform exploration of the Hilbert space means that these coefficients, the real numbers, and imaginary parts, each are coming from a random distribution, meaning they're forming a Gaussian. If they do that, then the histogram of CC dagger would be exponential, meaning that these probabilities that we mentioned would be exponential, and that's what we are showing in here. However, note that this arrow goes only one way, and there are other ways to get it from exponential. You cannot go, if you get an exponential, which we are getting in here, you cannot go all the way and claim it mathematically. But the other scenarios are less likely. So for an experimentalist, is it sufficient proof that indeed we have we are uniformly exploring all the Hilbert space, and the Hilbert space is needed. And the idea is that the 53 qubits take 10 million billion dimensional Hilbert space to do it. So there's no simplification around that. But there's one, so let me tell you what is next. We are going to consider a couple of circuits. Let me say, okay, first thing we want to show is the notion of fidelity. And by fidelity, we are going to compare what the probabilities of what we measure, what the probability what we expected to measure. So you have to go to a classical computer and compute it and compare these two. This is just a Shannon entropy, and you compare these two together, P dot Q or P log Q, it doesn't make much difference. And the rest that goes into formula is just normalization to be sure that, you know, when you're doing perfectly fine, you're getting 1, and when you're really tossing a random coin, your dice, you're getting 0. Essentially, that's what the fidelity is about. However, if you go to the paper, there are two differences. One is that you note that I have P of measured, meaning that a bit string appears sufficiently enough number of times that I can know its probability. But in the experiment, you would do 1 million or 10 million bit strings, and the Hilbert space is 10 million billion dimensional. So you're not going to see a bit string twice. So you have to just go from bit string to a probability of a given, from the probability go to the occurrence of a given bit strings, that's P of xi. And then also we are going to use ergodicity to make a simpler formula. So with the Porter-Thomas formula you see in the paper has several assumptions to it, becomes such a simpler form. Otherwise, it's the same as what you see up there. Well, we were lucky that the patterns that we apply gates can be two distinct patterns. We have a freedom, and one of them happened to be computationally easy, and one of them was computationally hard. And that should signal you that how fragile computational complexity could be. If you apply the gates in the order of A, B, C, D, this is, I'm showing you the entangling gates that you apply one sequence after another on a group of qubits. You can, when you've done going left, right, north, south, you can, when you go to the second cycle, you can repeat the pattern, or you can repeat the pattern in a different order. And it happens in terms of propagating the entanglement, these two are very distinct from each other, and would lead to a very distinct consequences. Okay, so, but computationally, one of them is very easy, which is what we have in the left, or rather easy, and one is, we don't know any way to simplify it, okay? So, but first things first, we are going to really split the qubits into two groups, left and right, and the left and right don't talk to each other. And we are going to run the sequence with a given number of qubits or a given cycle, given number of cycles for a set number of qubits. And we are going to monitor the fidelity I/O, and it goes down. And we can compute that because we can compute the numbers. What we can do furthermore is that we don't remove all the gates in between, but we only remove very certain selective number of them. And then still we can compute it for the easy cases, with the sequence of easy cases. And but for the hard cases, we just cannot. Well, I think we can do this. But when we go to the full circle, there is no way for us to do it on the right. This becomes extremely hard problem. And that is our claim for supremacy based on the numbers that we're obtaining from this curve. But what should be, but also there is one layer of simplification based on the fact that we are doing gates with certain fidelities, and we should allow the classical computer also to make errors and whatnot. To wrap up this story, I have to say that the recent result by Chinese outperformed our results. And there is another result by, and let me see if I have this. Sorry, I don't have the experimental result in here. But their result have gone to further depths and better fidelity. So they're holding the world record in terms of random quantum circuits with superconducting qubits. And the recent numerical result by another Chinese team is outperforming our simulation, because the quantum simulation, classical simulation, has been steadily improved. So what we claim that it takes 10,000 years, now it takes about half an hour. This 10 millennia is now, the community agrees it takes only 60 minutes, 30 minutes, and we are very happy to see that there is that much progress. And the whole idea is based on how to figure out to do these matrix contractions, tensor contractions, sorry, based on figuring out symmetries, or the order of contractions apparently matters substantially. What I want to talk, but I guess I would, well, I give you guys two options. So what is NISQ is about? As you notice, this experiment I explained was highly contrived. And so there are two ways to go from here. One is to make qubits fit to 1% or 0.1% error and make many of them and go for fault tolerant. Another way is that, what if we make the qubit slightly better, or just what we have? Can we solve some physics problem or some chemistry problem? And the answer is yes. There's certain problems that don't need that many more number of qubits, but need much better gates. Note that the vertical axis is getting exponentially harder to climb that axis. And that's the idea of I meant to be for this talk, but I'm a little behind. So and we have written several manuscripts, which is all a step toward this direction of trying to make better qubits and whatnot, and try to do physics or chemistry problems with them. And what I can talk to you next is if there is any hint of discovery, and I picked up one example. I meant to talk about that. So this is the team of people who contributed to this experiment I'm about to explore. Franco, what do you suggest? There's 11 minutes left. If maybe I pause, and if there is any question, I take it, and if there is no question, I can just go to this.
My vote is go ahead and just explain as much as you can, and then go on.
You know what? You know what we could do?
You can grab the airplane afterwards.
Yeah, let me keep talking. It's a bit rude. I'm going to talk for 11 more minutes. My colleague Trond Andersen, I talked to him a few hours ago. He was on his flight to Africa. He would be available to answer all your questions.
Okay. Whatever you think, just go ahead, and we're listening here.
Yeah, I think senior people probably know how to find me, and the students and those who are less familiar, they can have Trond would be there for the entire week. So I want to tell you so this is the group of people who focus on the time crystal experiment. I want to tell you what is the big deal. You have seen it probably in the literature. And I want to tell you what is actually the essence of it, and maybe, if time permits, maybe a few minutes on what we got. And you see, when you're thinking about the ordering, a spatial ordering. You can find a spatial ordering in nature very rather easily in large systems. You can have crystals, you can have liquid crystals, can have ferromagnetism, anti-ferromagnetism. You can find stable configurations of atoms or particles or systems that repeat themselves in a space. But if you ask, can I see patterns that repeat themselves in time? You can find some examples. You know, a person who is sitting on a swing and goes back and forth, this pattern could repeat indefinitely in time. Up to some caveats, Earth and Moon and whatnot can go around each other indefinitely in time. You know, a clock is meant to go indefinitely in time. But you realize that these systems that are repeating themselves in time have far less degrees of freedom. And what I mean is the following. If you get a lattice and you perturb it and you let it go, it would go back to where it started after some time. But let's say even you have a many-body system that oscillates very periodically, nicely repeat itself like a pendulums. It has not a single degree of freedom, but many degrees of freedom, let's say. But the problem is, as soon as you perturb it, it would not get back to where it started. And that is really the challenge, that it's rooted in the second law of thermodynamics, and that is led to defining something challenging, not impossible, to be defined as time crystal. Can we find a many-body system that it oscillates in isolation indefinitely? So you see on the top, I have a definition of time crystal, has 4 components, and the manuscript we wrote on this subject, which to show the time crystal is a stable phase of matter, we have gone over these 4 components and show them one by one in each figure of the manuscript. So read it carefully, please. You can see that there are 4 components. It has to be an isolated system. It has to be many-body. The example I have in the lower left are few bodies, and it has to oscillate indefinitely, okay? Of course, we can get only close to isolation and whatnot, and that's really, you have to accept my words for it. So here is the challenge I'm pictorially communicating. If you have a system which has 2 stable configurations and goes between 2 of them, the second law tells you that it's very likely scenario, right? It doesn't tell you it's impossible, but in entropy, an isolated system cannot reduce, right? You have many degrees of freedom. Entropy cannot reduce. Entropy in the universe cannot reduce, but can stay constant. But experimentally, staying constant and not increasing is a very challenging scenario. And that is the core of the challenge of seeing a many-body localized, of seeing time crystal phase, which comes as a result of having a many-body localized case. I'm gonna skip this one. Let me see. So the key that came to remedy and help us was the notion of many-body localization, and the proof that is theoretical that many-body localization is a stable state of matter. It's not a thermodynamic phase, so you just have to accept it's a stable state of the matter, which means that it does not, and then you go to a Floquet driving of the system, it does not absorb heat from this Floquet system because it's many-body localized, and the net flow of energy to this system would be 0. So it's not heating up, it's not going to become unstable, and thanks to many-body localization, it would remain stable. So essentially, to show that you have a stable discrete time crystal, you have to show that you have many-body localization. And that's the physics. Okay. And again, this is a maybe encouragement to read the manuscript. First, we have to show it's a stable phase of matter, meaning that it appears over a range of parameter space. Then I have a hard time of showing that I'm dealing with a closed system, which we don't have in the lab, so we're just going to argue. And then we have to show that we have eigenstate ordering, which is the signature of many-body localization. And then we have to take to a much bigger system to show that, you know, in the thermodynamic limit, it stays. So let me just tell you the pulse sequence we used, and then maybe just hint of the experiment. Here is essentially we have a kicked icing model, kicked transverse field icing model. There is no Hamiltonian. We have a unitary operation. We rotate the qubits. We let them interact with icing coupling, and then we disorder and detune them, and we repeat this cycle over and over again. So it's a Floquet dynamics, meaning we repeat the same pattern of drive over and over again. And you can see this is exponentiating of these different terms that are essentially, you're probably familiar from your Ising Hamiltonian case. And you just repeat these terms together. And let me just turn off the coupling, maybe some interesting aspects of the experiment I can maybe say very briefly. Let's turn off the coupling. So you have 20 qubits, they are independent from each other, and you kick them with a rotation. You apply X gate to them. So they're just going to go up and down, rotate around their Bloch sphere. There are 20 independent problems, and that's what you get the top row. When G equals to 1, you go from north, you start from North Pole, you go South Pole, and vice versa, you keep going. And when you Fourier transform, you see a peak. But if G is imperfect, it would take you many cycles to come back. So you have two beating frequencies, and then when you Fourier transform them, you see two peaks. And that is a single math exercise for you, simple math exercise that you can see that would be the case. But something interesting happens right in here. As soon as you turn on the interaction between the qubits, it gives some rigidity to the phase. And then you see, regardless of the value of G, you get single frequency back. You're really locked there. It means that you see some phase locking in the down to result of interaction. This phase locking is not a quantum phenomena. We are familiar with it. Animals, when they are synchronizing, human beings, when they're clapping, all do this synchronization. And it has been observed by other researchers in the lab. But what the key to show the physics is to show that we have actually many-body localization, and this many-body localized phase is stable. And that was really the essence of what went into this work. Otherwise, showing that you have phase locking is really not the proof of having a discrete time crystal. It would not be, it's not a quantum phenomena to be, let alone, well, it could be a phase of matter, but it would not be a new phase of matter. That is not possible in the classical world. But maybe the most touchy point of the experiment was this in here, that I have an open quantum system at the end of the day in the lab, meaning that the qubits are connected to their surrounding. So I have to remove the effect of decoherence. And that was done by some clever echoing, that you see there is a signal and there is a nominally identity signal, which dividing them by each other allow us to remove certain errors, and we can show at the lower panels very stable oscillation for a long period of time. And the rest is, again, emphasizing on being that we have localization and whatnot. And last but not least is to show that when you look at the larger and larger scales, you get a better performance, and the ordering does not vanishes, meaning it gets more and more amplified. So here there is an order control parameter of the phase transition, and the vertical axis is the order parameter. And you can see that when you go toward the one side of the phase transition, this order parameter grows, and the other side it reduces and points to a crossing point, which is very close to what you anticipate from the numerical values. So maybe I stop here, and if there's urgent questions for a few minutes, I take them.
Any questions?
Thank you very much for very nice presentation. Let me see, there are here some questions in the chat. I don't see.
I think I scared people.
No. I think this was like a great. Well, you had a diagram where you had full circuit, elided circuit, and patch circuit. I know patch, you're separated left to the right. That's clear. What's elided circuit?
Sorry, I forgot to say that. Elided means that you you eliminate certain gates only for a few, where you eliminate that row of gates for the very few cycles. Let's say here M is 14 on the left, meaning you have gone up to 14 cycle depths, but on the first fifth cycles, you did not apply it. And from the fifth cycle onward, you apply that gate. So you have two systems which are not connected for a while, and then they later on, they get connected to each other.
So the patch, so it's initially a patch circuit, and after a few cycles, let's say 5, then they become a full circuit. I see.
Yeah.
And,
sorry, I should.
No questions?
I had many questions, but I can ask you some other day separately. So I'm waiting for other people to ask questions here. It's there are more than 50 people in the audience, even though it's late. So there are people in the Zoom plus the people there in Kigali. So there would be like it's quite a few people listening there, even though the time is a bit late here. Here is about 2 in the morning here. So, Omolulu, do you have any questions? Or in the audience there?
No, there is.
Oh, here it is. What time crystals has to do with quantum speed up in computation?
I don't think it has much to do. It's is the mode of discovering new phases of matter using a quantum processor. And these computations, in this particular case, not, but generally, knowing, understanding phase of matter could be a very computationally costly. And if you could rely on the geometry and the whatever the quantum processor offers you, you could do it as a good quantum, as a processor to study physics. It's not necessarily a given computation. The question was, can a time crystal be a stable phase of matter? And that was what we tried to answer in this case.
And the next question by Itamar Halevi is gapped versus non-gapped role. So what's the role of the gap?
I'm not sure what the question is. This is a unitary Floquet dynamic, so we are not talking about the ground state. There is the eigenenergies are point on a unit sphere, on unit circle, and all the eigenstates of the system have the same property. So you don't need to be on a ground state. And here there is a Floquet dynamics. There's no Hamiltonian.
I see. Okay, so therefore, but essentially the dynamics you have is more like described by Liouvillean, no? Because it's interacting with the environment. So there is the Hamiltonian part plus all kind of Krauss operators. You have a full Lindbladian kind of thing.
On one of the figures, which I jumped over rapidly, I meant to say that we figure out how to experimentally cancel and remove that effect. Yeah. The idea is that by echoing, you can cancel it. You're right. That's a full description, but we hope to try to get by without doing that. And the idea is that
by canceling, I see.
Yeah, is a spin echo for a large system, is an echoing system for a large system. You can divide the blue signal on top to the black signal on top, and then you get the blue one in the bottom, which is saying that you can somehow cancel these effects. Yeah. That was the thinking.
Okay, these are all exciting results. So
Maybe, yeah, I would say Trond would present the latest and greatest, so stay tuned with him for him.
Well, is he logging now or what?
No, whenever his time comes, actually he'll be physically present in Africa.
I don't know, he's giving the talk, Trond is giving the talk tomorrow. Trond
Okay,
Andersen.
yes.
It will be at like around noon or so.
Yes.
Kigali time. So,
All
okay.
good.
So I think we don't want you to lose your flight, and we thank you for the nice overview of exciting results you have there. And then
Yes.
I don't know. I have some questions, but I'll ask you separately, like in a few weeks after a few deadlines here.
Sure, of course. Sure.